Leonardo da Vinci did that. He did sort of a mirrored script,
Oh yeah, I remember.
something like that.
Where he stood up with the mirror and then he could do it.
Right. Okay. Actually, I think he may have trained himself to read mirrored script. Let's look at those readings. There are two types of waves that we demonstrated briefly with the Slinky, and then you had in reading. It says sketch each and discuss their differences. So the first one, the most wave-looking one, looks like a sine, or if you prefer, a cosine wave. Not so much a tangent. Sine or cosine, though, and then we've got in here. How do we define a wavelength with? Well, first off, what kind of wave? Which one is it? Yep. I had heard a couple, but yes, transverse is. Okay, so how can we define a wavelength on this?
From like the peak to the peak or the trough to the trough?
Yep, either of those would be fine. Any point on the wave to the same point on the next wave, we call a wavelength. So from here to there is also a wavelength. We're not going to be dealing with anything that's changing this wavelength as we go, really, unless it changes all of them. All right, the other thing was amplitude, which is a measure of how strong or how much energy is in a wave, indicated where?
Peak to trough.
Not peak to trough.
Peak to middle or trough to middle.
Right. Either of these will be an amplitude. And this is going to be when we talk about, well, we aren't going to be getting into intensity and that sort of thing, but intensity is related to this and just how high or low. And obviously my line should be straight across, of course, but so that this distance is the same. But it's just one of them, like so. And then we had longitudinal wave. So actually, how does a particle move that's in a transverse wave? Up and usually up and down. So in a circle is, and we'll talk about that in a moment. So the motion here is just up and down. You're referring to a water wave, and a water wave is a little bit different. It is very close to a transverse wave, and it certainly has this look. But because it's instead of going through a medium, because it's at the surface between two media, the particles actually do move a little differently than you'd expect. They move in a circular fashion. Let me see in the book to make sure I get the right direction. I know some of you indicated this, and I think this clockwise. Okay. So a particle like this moves clockwise if it's a water wave. And the reason for that is in order to get more here, you have to more in this place, you have to displace some of them. And then they have to go away when you've got the minimum. They can't just all compress, squish together closer, or expand farther apart. It doesn't work in that way. So that's a water wave. Now, the longitudinal wave is tougher to draw. So there are a few different ways to draw it. One way is just with some vertical lines. So you've got some places where it's stretched out, leading to some places where it's squished together, and then it stretches out again. I'm not intentionally making these taller or shorter. It's just because they were closer together. We've still got wavelength, which goes from one part of the wave to a similar part of the wave. If I had drawn it small enough, we could have gone from this part to the next part. What are these different parts called? That wasn't in the reading, but maybe it should have been. What is the part where it's stretched? We've got parts where this is stretched out, parts where it's pushed together. Period is a timing thing that we'll talk about in a moment. We've got rarefactions here, where where it's stretched out. So when we think of this like a slinky, this is the part where the slinky coils get closer together, and compressions. And there are other terms, I think, that go along with these in the text. But it's alternating these, and it's a continuum. So sort of like this doesn't go directly from high to low. Likewise, this doesn't go directly from stretched out to squished. It's a continuum. So it will, as this squished part travels, right around it will be slightly less squished, a little bit less, until it gets to stretched out. So this is how sound waves travel. So it's a pattern of squished parts and stretched parts in the medium, in the air or in the water or whatever. Can travel through solids as well. It's very hard to talk through a solid, but that's something else entirely. The sound itself travels very, very quickly. This one, it's really hard to define what amplitude is, and so normally we don't, at least not from the wave. But it's a measure of how squished and how stretched the medium gets. And we're not going to be getting into that, but a louder sound has a greater amplitude. It squishes them more or less. Now, on to Zach's question about the period. All of these waves have some things in common. Number one, they all have wavelengths. Represented by the Greek letter lambda. They all have periods, which is always in physics a capital T. This is the time it takes to repeat something. Right? So it's from one point back to that point. And this is usually in seconds, and then we have frequency. And a frequency is 1 over the period, and it's measured in hertz. Abbreviated HC. So a frequency of 1 hertz is something that repeats itself once every second. 60 hertz, 60 times per second. Yes?
The wavelength and the period is
Wavelength and period are not the same because this is typically in meters. It's the actual distance, if you could measure out from one point to another, and this is the time. These combine, though, to find the speed that the wave is traveling, because if you know the distance that it's traveling divided by the time it takes to do that, you have a speed. And since the frequency is 1 over the period, not quite a line there, we can also just say that it's lambda times the frequency, the wavelength times the frequency. And this goes for any traveling wave. Usually we'll use this one, but this one can be useful in some circumstances as well. That's one of the big equations we're going to get. The next is related to my string that I've got out here. And you read a little bit about waves in strings. I'm going to, hopefully the video will turn out okay here in a vision of the class. Oh, it's hideous. Okay. And this string has a weight tied to this end. I've got it on a pulley over here so that the string can move backward and forward a little bit. And then this thing over on this side is an oscillator. So when it's plugged in and getting electricity, it goes back and forth. Let's see, can I see that screen while I'm yeah, should be okay. So I'm going to turn on my generator over here. You hear it buzzing there. Nothing much to see right now, but what from the reading, what kinds of things affect the waves in a string? Tension of it and the mass and length, mass per unit length. We can not change the mass a lot, although by pulling on this, since it is slightly stretchy, we are changing the amount of mass per unit length a little bit, not too much, but we can certainly change the tension on it. So I'm letting up on the tension right now, and at certain parts you can see it certainly is going to vibrate a lot more with less tension here. And at certain points I can apply just the right amount of tension to get standing waves. So standing waves are waves that repeat themselves within vibrational system like this string or your bottles. So in the string, let's just see. I can sometimes get lots of them. You can certainly see it moving. And at some points, that's pretty good, where you can see peaks and troughs at the same point. But now as I increase the tension, you'll see it vibrate sort of willy-nilly, but then settle on one set of waves. Next one. What's happening as I'm increasing the tension to the waves?
The wavelength is kind of more spread out.
So a longer wavelength. It's taking up more and more of the string. And at some point I start overloading my system here and it's not vibrating quite enough to do it anymore. But we can see just by pulling on this that we're getting different amounts or wavelengths up there. And let's see if I increase my amplitude a little bit. So this works basically like a speaker that vibrates the post up and down. This is a neat lab, but I unfortunately only have one of the devices there. No. Oop. Nice. I'm not going to get any more out of there. Did I make it in?
Yeah.
I am the greatest ever. You gotta admit, that was a pretty awesome shot.
You're going for, right?
That is exactly what I had planned.
And he just break it to you.
Yes, I'm not worried. It has served its purpose for today. Yeah, I know.
We know.
We're gonna move past it. So when we are describing a wave in a string, we've got a specific formula that relates each of those things. Let's bring it over so I get it right. I can't find it, but it's related to the tension in the string. And let me see, I'll have to correct this most likely. We've got on the bottom of this the linear density, mass density of it. So it's how many kilograms per meter is it? And let me just make sure that I'm getting the right formula on top. Oh, yep, sorry, other way around. The speed of it, that didn't look right, is related to the ratio of the tension and the linear density of the string itself. so that as I am applying my a greater force, the speed goes up. Well, if we look at our formula here, the frequency of this was governed by the oscillator itself, and that wasn't changing except perhaps when I changed the amount of voltage going to it. But that wasn't changing. So if the speed goes up, it must be the wavelength that's going up, which is what we observed. We had fewer and fewer nodes in there. Likewise, if I had increased the mass of this string somehow, the speed would go down, which means the wavelength would go down. Because again, the frequency isn't changing. We had, in your reading, you had questions about both of those. They were both related to Ohm's law, or to Newton's second law. If you increase the tension, it increases the speed because F equals ma. If force goes up and mass doesn't change, the acceleration must go up. Essentially, it's each individual portion is pulling a little harder on the neighboring portion, which allows the wave to pass through it more quickly. Likewise, if your mass goes up, but the tension doesn't change, then the acceleration, the speed of the wave must go down. You could drag twice. So these two are our formulas are what we're going to be applying in different ways for the first problem set. Before we go out, I want to just highlight the fact that you have been working on standing waves in sound in that experiment, in the bottle experiment. So this is related, that when you set up a vibration in the bottle, you are getting some standing waves, so some equal number of waves or half waves set up in this bottle, and that's what we're trying to learn about. Hopefully in some of your research you've seen that instead of the string vibrating at a specific frequency, you're getting the air column to vibrate in a specific frequency, and because it's doing it so much, that sound is amplifying itself. So it's like the waves here that were stacking up, interfering with each other and making themselves that much stronger at certain points. Okay. Any questions before we move on to the quantitative part? Okay? Yes. Yes! No, you said that wrong. Quantitative means math!
No, I definitely meant quantitative means math.